So let's discuss how to find Laplace transform of a periodic function. A periodic function we discussed in Fourier series. If a function is periodic, it should satisfy this equation where p is greater than 0 or real number, a period, real number. This is the definition of a periodic function we know. So to find the Laplace transform of periodic function, let's have a brief theorem. Let ft satisfies the condition of the existence theorem. And the condition of the existence theorem are: number one, ft is piecewise continuous, and the other is ft is of exponential order. If a function satisfies both of the conditions, it should be piecewise continuous as well as it is of exponential order, then its Laplace transform exists. So the theorem states if ft satisfies the condition of the existence theorem, and it is a periodic function and is a periodic function with period p greater than 0, a real number, then so these are the conditions, then its Laplace transform exists. And given by Laplace transform is equal to 1 minus ps, where p is period this time, 0 to p e minus st f of t dt. This is the theorem. Let us prove a few steps so that you will get how you will get this and how you are going to have p there. So we'll prove in a minute. So proof. So ft is piecewise continuous as well as exponential order. Further, it is periodic. Two things are given. We know that Laplace transform of a function by definition 0 to infinity e minus st ft dt. This is the definition of a function whose Laplace transform exists. So this right hand side I can write 0 to p e minus st ft dt plus p to 2p e minus st ft dt plus 2p to 3p e minus st ft dt plus so on and so forth. So 0 to infinity I can separate up 0 to p, p to 2p, 2p to 3p and so on and so forth. This is first integral. This is second. This is third and so on and so forth. In first integral, replace t by u. T by u. So where there is t, you are replacing t by u. Here the limit are on t. When t is 0, u is 0. When t is p, u is p. So in second integral, replace t is equal to u plus p. In third integral, t is equal to u plus 2p. Now the first integral. First integral 0 to p e minus su fu du, because we have replaced t by u and dt is du. For the second integral, so the limit are 0 p to 2p. this is, if t is p, the lower limit t is p, u will be 0. And if t is 2p, u will be p. These are the limit I have. Minus s u plus p. U plus p f of u plus p du plus. This I have replaced t by u plus p. And p is the period. So it is constant, a real number. This is a variable. dt is du. In the third integral, I am replacing t by u plus 2p. So the lower limit of t is 2p. If I am putting 2p there, u will be 0. And if I am putting 3p here, u will be p. E minus s u plus 2p f of u plus 2p du and so forth. So this I have. Since f of t is periodic, f of t is periodic, that is f of t is equal to f of t plus p is equal to f of t plus 2p and so forth. So we have seen if p is a period, then np, where n is an integer, 1, 2, 3, 4 is also a period. So the above equation becomes this one. This is equation. On the left hand side, I have taken f of t, and this is 0 to p e minus su f u du plus 0 to p e minus s u plus p f of u du plus 0 to p e minus s u plus 2p f of u du plus so and so forth. Since it is periodic, f of u plus p is f of u plus 2p is f of u. So I have it. Something is taken common, which is su, fu, du. This is taken out. If this is taken out, I left with 1 plus e minus ps, e minus 2ps, e minus 3ps and so forth. This I have. And what is this? What is this? This is a geometric series. Geometric series with first term 1 and common ratio with first term 1, a is equal to 1 and r, the common ratio is e minus ps. This is the common ratio. You are putting this in the numerator dividing by this in the denominator dividing by or this. So you get r is the common ratio. Since this is sum of the series, it can be written 1 minus r, which is 1 over 1 minus ps. This is going to be the sum. So the sum is written 1 minus ps 0 to p e minus su fu du, or u can be replaced by t because each time our function is in the form of t. Minus ps 0 to p e minus st ft dt. So this is the formula for finding the Laplace transform of a periodic function whose period is p. So do not forget to write down this as it is. So couple of examples. Find the Laplace transform of the following. Functions. First is, suppose, let me write 4 pi square minus t square, and f of t plus 2 pi is f of t. Look at that. This is the definition of a periodic function. It means p is 2 pi. 2 pi is the period given. And if you are sketching this function, might be your sketch will be something. Sometime you are sketching, sometime no. 2 pi, this is 4 pi, this is 6 pi 0. When t is 0, it is 4 pi square. When t is 2 pi, 4 pi square, 0. So it is going to be. And then it is going to be. And then it is going to be. And then it is going to be. So a periodic function, obviously this is going to be the periodic function you have determined. You can find the Laplace, since it is periodic, you have to find Laplace transform by applying this formula, where p is 2 pi. Let me have a few more, then I'll solve one for you, which is t. T lies between 0 and 1. And f of t plus 1 is f of t. Look at that. It means this function is periodic. Let me sketch that function. It is t, this is 1, 0, this is 2, this is 3, and so forth. Here f of t. F of t is t. When t is 0, when t is 1, it is 1, so this is a linear function. Since it is periodic, it is moving like this. So a sawtooth wave is going to be there. You have to find its Laplace transform where the period is 1. Third one is f of t is equal to, let me have a graph. This is A, this is 2A, this is 3A, and this is 4A, and so forth. So this is 1. This is minus 1. This is 1. This is minus 1. And so forth. It's going to be here 0. This is f of t. From the figure, can you find what is the period of this function? If you are looking at the diagram, can you find the period of the function? This is minus 1. F of t plus 2a is equal to f of t. Look at that. Because it starts from 0 to a, it is 1, and then from a to 2a, it is minus 1. And then 2a to 3a, it is 1, and then minus 1. It means a square wave whose period is 2a. And if you are solving this, for example, Laplace of f of t, 1 minus 2as, p is 2a this time, 0 to 2a, e minus st, f of t dt. Now in this diagram, which is a piecewise continuous function, because there is a jump discontinuity, so 0 to 2a, you have to split up. So how would you split up? 1 minus 2as is p, 0 to a, then plus a to 2a. Look at that. 0 to a, your function is 1. This is 1. 1 e minus st dt plus a to 2a, it is minus 1 e minus st dt. And you are integrating upper lower limit, solving, simplifying, finding the answer. One question I will solve, which is a little bit, you actually know how to integrate using tabular integration. Find the Laplace transform of f of t is equal to sin t when t lies between 0 and pi, and this will be 0 if t lies between pi and 2 pi. F of t plus 2 pi is equal to f of t. This is the question. It means if you are just imagine, you will see it is half wave rectification. T. This is pi and this is 2 pi. This is 3 pi, 4 pi, and this is 0. Here f of t. When t lies between 0 and pi, the value of the function is sin t. Let me sketch. When t is 0, sin is 0. When t is pi, sin is 0. Let me have in between pi by 2. When t is pi by 2, sin is 1. So our graph is like this. The other half, when t lies between pi and 2 pi, the value of the function is 0. It means the negative half clips off, that vanish. And since it is periodic, look, 2 pi is a period. Again it is sine wave and then the 0. Again it is sine wave, then it is going to be 0 and it is moving like this. So this is half wave rectification. So let me solve 1 minus Laplace transform of the periodic function is 1 minus p. P is 2 pi minus 2 pi s, because minus ps is in the formula. 0 to 2 pi e minus st ft dt. This is going to be the formula. Now 1 minus 2 pi s as it is. Look at the graph. 0 to pi it is sin t and pi to 2 pi it is 0. I am breaking up the integral 0 to pi. E minus st sin t dt plus pi to 2 pi it is going to be 0. Correct. Pi to 2 pi is 0. Now I am integrating this two functions where none of the function is going to be 0, either by taking the derivative or integral. Any function, you are using tabular integration. Let me have any function on the left hand side. You can have any function. I am integrating this. The derivative of the left hand side and the integral of the second. The derivative of left hand side and integral of second. And you have to stop here. Stop here. Because this function is going to be the same and this function is going to be the same without looking their coefficient. You have to stop. Once you stop, you have to like this. This put a plus sign, a minus, a plus. And there is the horizontal line. This line is horizontal where you stopped. I am solving this integral e minus st sin t dt is equal to separately. And then I'm putting the value back here. So look at this. The limits are 0 to pi. If I am putting pi there, sin pi is 0. And if I am putting 0, sin 0 is 0. So this vanish. So I am not writing this. I am writing multiplying these two, which is minus e minus st cos t. The limits are 0 to pi. That I am writing. I am multiplying these two with minus, plus multiplied with minus is there. And then the horizontal line I am writing in terms of integral again. So this minus is multiplied with plus. So it becomes minus and s square is there 0 to pi e minus st sine t dt. Look at that. So the horizontal line is written in terms of integral. Minus s square is taken out and the function r. So this whole term is taken there. This is 1 plus s square integral 0 to pi e minus st sine t dt is equal to minus. That whole term minus s square is coming to 1 plus s square and this is taken common. This minus is taken out, t is replaced by pi everywhere. E minus pi s cos pi minus t is replaced by 0, which is 1. Cos 0 is 1. So this is minus e minus pi s minus 1 minus 1. Cos pi is minus 1. So let me multiply with minus. So this is 1 plus e minus pi s. So 1 plus s square integral 0 to pi e minus st sine t dt is equal to this. This implies 0 to pi e minus st sine t dt is equal to 1 plus over 1 plus s square, because 1 plus s square is dividing on both sides. So this is the term or the integral you have to show your working separately on a piece of paper. This, when none of the function is going to be 0, by taking the derivative, you can have sin t there or you can exponential there. It depends upon you, you are getting the same answer. Once you integrate, after one step, the next step you have to stop. Because these functions are identically the same without looking their coefficient. You have to stop and then the same procedure, this multiplied by this multiplied by this, and the horizontal line. Horizontal line is written in terms of integral, which I have written this. Putting this there and after simplifying this. Now, this you have calculated. So Laplace transform is now 1 minus 2 pi s, and that is this 1 plus minus pi s 1 plus s square. If you are leaving the answer there, that's okay, but if you can simplify a bit further, that's okay, you can do it. This is 1 plus e minus pi s 1 minus pi s. A plus b, a minus b, and if you are applying the formula, you are getting this thing back. So this is 1 plus s square. So if you can cross this, this is 1 over 1 plus s square 1 minus pi s. This is going to be there. So that's all for the Laplace transform of a periodic function, because the rest of the function were simple. You can integrate with one is the polynomial whose derivative eventually vanish, but here I have taken one is the exponential, one is trigonometric, so that you have learned a tabular integration method to proceed the way you can. And you have to show this integration separately, and then this is the result of your integration, putting back there, and after simplification this is the answer.